So the first speaker is Paolo Amore. Amore. Yeah. So as you can tell by the shape, curved hexagonal packing. So 20 to 30 minutes.
Okay, thank you. First of all, I would like to thank really Ariel and Simon and all the people here that have been very kind in inviting me. Also the Isaac Newton Institute. What I'm gonna talk about is a topic that we invested researched in the past few months. The outline of the talk will first cover hexagonal packing in the hexagon and curved hexagonal packing in the circle, which are known topics. And then I will move to talk about curved hexagonal packing in regular polygon. That is something we found out. And I will describe an algorithm which I call the deterministic algorithm, because we started this work doing computational programming, but at the end we found out the way to crack the problem deterministically. So I will show you that. And finally, a few examples that don't fit this curved hexagonal packing certification, but are still interesting. Okay, so packing the hexagon, well, everybody here knows that, so I could really be fast here. Essentially, in the infinite plane, you can have a perfect hexagonal packing. That's the maximum density that you can even reach. And once you put a container, geometrical frustration limits your possibility. But if you have an hexagonal container, for example, at certain number of disks, you are lucky enough to recover a perfect hexagonal packing. So these numbers are called, for this reason, hexagonal numbers. So here you see two examples. This is 7, 19, 37, 61, 91. So you can keep going, because essentially in this case, you tend to the continuum in n for n going to infinity. Actually, you can also extrapolate the sequence. These kind of numbers are called hexagonal numbers. So they are like the magic numbers of the hexagon. And K is also the number of shells inside this hexagonal packing in the hexagon. Okay, so quite a bit ago, 1997, Graham and Lubachevsky discovered that in the circle something similar appears also. And they found out that, well, this is the hexagon, we just saw it. They found out that in the circle, you can also have, at this particular hexagonal number, you can also have hexagonal packing. It's not the very same, it's curved, okay? So you have the very same shells, with the very same number of disks. They are slightly bit smaller, and you can see from the density here and the density here. And well, there are plenty of those. Essentially, they also gave a formula. I don't know if I put it in the slide. I think I did. Yes, they estimated that there are k minus the maximum between k minus 1 over factorial over 2 and 1 equivalent configuration in the circle, which means a configuration with the same density, all configuration with the same density. However, they discovered, this is easy to do, that starting 127, you lose optimality. Curved hexagonal packing still exists, but it's not the best you can do. And also in the limit of k going to infinity, very, very large number of shells, you get to this density, which you may recognize is the square of the density of hexagonal packing. So it's a very nice thing. So a few months ago, in November, I was completely taken by computational programming, trying to, I did an algorithm to pack in the hexagon, in the polygons. So at one point, I was starting to see that something funny was happening when for certain regular polygons and for certain numbers. So essentially, polygons have a number of sides multiple of 6, And exactly at the hexagonal number, at this in this condition, you find that there are very nice configurations. And the number of these configurations immediately appear to be growing very fast. So you will have many configurations with the same density, all very pretty. And of course, that was also a problem because at the beginning, I had this year I was lucky enough to have two very bright undergraduate students. So I proposed them to help me out. At the beginning, the plan was, let's try to do everything computational. And that was a nightmare because computational finding all the symmetric structure out of computation would be out of question. So eventually we managed to do otherwise. So the plan that we managed to apply was to build all the CHP, the curved hexagonal packing configuration in certain regular polygons in a deterministic way, using an algorithm that we have devised and we actually call deterministic algorithm. So the idea is pretty simple. Actually, the algorithm was pretty simple. You start looking at the border, and you start looking at 1/6 of your regular polygon, because you look for hexagonal symmetry. So 1/6 is enough. And the first thing you can notice is that you can start from, you see the polygon on one side, and then you start putting the centers of the disk along these positions, with the condition that once you get here, for example, this has 1, 2, 3, 1, 2, 3, 4, and 5. The fifth point, which will be at the starting of the rotative region, you have to impose the appropriate condition. So you actually can calculate this point exactly, no approximation involved. So you can actually know exactly the position of your coins on the board, if they are coins. So from that, you can actually see that the formula gives you, sigma here is the number of sides of the regular polygon, gives you a relation, two relations that have to be fulfilled. And from that, you can calculate the density of curved hexagonal packing analytically in terms of sigma. This is the density of the circle in the circle that was obtained by Graham and Lubachevsky. And actually, this is the result that Graham, this is our formula for K going to infinity, which means the very, very dense domain. And of course, this density, unfortunately or fortunately, is always much bigger. For K going to infinity is much bigger than the density of P over square root of 12. So, okay, so we can know the density, but can we know something more? So, what I want to point out is that this point, I will characterize this point in terms of these angles. Okay, these angles are the angles that these arrows form with the horizontal line. Okay, so phi 1, phi 2, phi 3, phi 4, and so on. Well, in this case, only phi 4. So for a regular polygon, essentially, I can exactly determine where these points are. So I can exactly determine all these angles. For a polygon with K shell, these are K angles. And from numerical calculation for the dodecagon, we started finding out that the number of possible degenerate states in the packing fraction was growing kind of large, okay, like this formula here. This is empirical observation, okay? But then we realized that we could do the things in a more systematic way. So how do we do it? So once you have set the border, you work with this is, I think, an octadecagon. You can set your border coins in a unique way. That's common to every configuration. And then you start from this point. It's a convention. We start from this very point, and we trace a line of segment that joins this point to the very center. Okay, so we actually think of in terms of the new angles that before I had the angle phi, which were the angle between these arrows and the horizontal. And now I have the angles that I call psi, which are the angle between this segment and the horizontal. Psi and phi are different angles, but they are related. So yes, they are related. And yes, one thing I can also realize is that if I take this octadecagon and I reflect it, I don't get a new configuration, right? So if I reflect it, let's see, like this, I don't get a new configuration. So from this, I get some relation under the transformation, this angle psi transforming different angles. This argument, I needed to purify all the possible configurations from repeating themselves, right? So one other thing that is very important to keep track of the result is to use a notation. So the notation that we are using is a lexicographic notation, which means that we are going to call a segment of kind A when its angle psi is the smallest possible in the set, of kind B when it's intermediate, and kind C when it's the largest. Of course, you can realize that I can sit this octadecagon along three different sides, right? So if I were able to rotate it so they sit on this side, I would see a different line. And also if it rotates on this side. So essentially, this means that these three configurations are the same configuration, right? Okay, so I should not overcount it. These are the degenerate configuration that appear. So now, there is a conjecture at the basis of our algorithm that maybe it's very simple, maybe not, I don't know, but it works, but we have no proof of it. So the conjecture is that the set of angle psi is just a permutation of this, of the phi plus P over 3. Okay, so it really means that when you think of this black line joining the corner with the center, is not arbitrary. There are very special conditions that have to be met. So I don't know, maybe it's simple to prove, I don't know. But if you do this, then there are all kinds of things that you can take into account. First of all, you use lexicographic order. When you have several configurations that are all the same, by convention, you use the configuration which start with an A and will always lexicographic order. So you make things simpler. Reflection is actually an operation that inverts the lexicographic order. Then you have to keep into account degeneracy. For example, certain configuration can appear in different flavor, but it's the same configuration. So we actually group, we can partition the group with each own with its degeneracy. Then we have another variable that is the number of occupied vertices, because depending on the kind of packing, you could have vertices that are occupied or unoccupied. And then in special cases, the reflection produces a configuration already obtained or otherwise, so that also enters. So when you do this, you actually can come up with a formula for a non-equivalent CHP configuration. This formula, which actually in the limit, in the proper limit, becomes the formula of Graham-Lubachevsky. So how does the algorithm work? The algorithm is pretty simple. First, you start identifying the border points, the one I started with. Then you pick a particular permutation of the angle. This is the conjecture. Then, as a result of step 2, you start putting your points or circles in the domain in a way that is better to show it like this. So I started putting the coin here, then I put this one, okay, then I put this one, this one, this one, this one, this one. This means having a particular guess for what we called it DNA because it specifies completely what is there. Once you put this sequence here, everything comes out automatically. You don't have any more freedom. Essentially, the algorithm, what it does is just look where to place the next coin, and so on and so forth. And you just need to work on 1/6 of the pizza because the other ones come out of rotation. So essentially, it was pretty fast, and essentially, it improved quite a bit our. Didn't work. Well, I have, yes, if it is possible. It was working a few minutes ago.
Yeah.
Then it's.
So 10 minutes to go.
Yes. Oh, so this is. Oops. This is a particular sequence. Okay, so you start putting the coins on the border. You work on 1/6 of the domain. You keep filling, and then when you have filled the 6th, you rotate it. Okay, can we show already the other presentation so you don't have to? This is an example of configuration in a dodecagon for, I think, 7 shells, I don't remember. These are the direct diagrams, and these are the Voronoi diagrams, okay? So these are, this is dodecagon for 217 disks, which means it's not optimal anymore. It's like nice, but it's not it's surely not the global maximum. Okay, so maybe, yeah, I think I can switch back to. So here there is a table. We have material, supplemental material in Zenodo with thousands of configuration and graphs and everything, and tables on the paper. We have tables up to, I don't remember how many sites, but here is a quick just table for the dodecagon and the octadecagon. Here you see number of shells. The important part is here the how many configurations were built with the deterministic algorithm, how many configurations come out of our formula. Okay, they have to match, of course, if it works. Okay, so in this case, for the octadecagon, for example, a shell, there are 2,520. But I remember that there are cases where we have calculated more than 20,000 because it's very fast once you have the right way to do it. So I suppose this is not going to work either. It didn't work. So we found this is CHP, but we found something interesting and unexpected. So this is a non-argon, and this is a regular polygon with 27 sides. And the 37 is an hexagonal number. So the non-argon doesn't have the symmetry of the hexagon. If you rotate it by p over 3, you don't get the same domain. Yet, the configuration that inside this domain, it does. Okay, it's a very special because it's a curved hexagonal packing in the non-argon that I wouldn't expect it to be there, and it is there. So, and also for this other guy that 27 sites, I don't know what his name. At one point I learned it, but I forgot it. And then there are still other beasts that they are like, they want to remember the hexagon. These are different numbers. These are not hexagonal numbers. They still show up. So my conclusion is that the hexagon doesn't want to go away. It still wants to come back and play a role. So once you get to a very large number of shells, then of course CHP is not the best thing you can think of, but you can still find a use for it, because if you think about it, it's a very regular covering of your domain. And maybe if you do computational work, like I like to do, you can use it to find better configuration. So this is a used configuration of 1,657 circles. I put it in my algorithm that does some kind of perturbation, and then let it evolve. It evolved to a much denser configuration with just one only shaping, one only run of the algorithm. It ran into a very large, much more dense configuration. Actually, for this kind of case, with this kind of case, there are how many? 8 million, more than 8 million possible CHP. So this is just one of those. I suppose they perform more or less the same. This is the Voronoi diagram of the configuration. So you see that nice thing is that in the original configuration, you have a lot of hexagons, some squares, a lot of squares as well. But once you leave things to the algorithm, it really leaves all the hexagons inside, almost, and it pushes all the pentagons and heptagons and squares on the border, modulo these lines of heptagons. And the blue, light blue are pentagons, the violet ones are heptagons, the green ones are squares. So, conclusion, curved hexagonal packing exists also in regular polygons. There is an algorithm that can build all the hexagonal packing you want. We don't have a proof that conjecture. It would be nice to have a proof of it. Maybe it's something trivial, but I don't know. We have a lot of supplemental material if somebody is curious about it. And I reiterate that I'm very grateful to all the people here. They are really very, very kind. But I would like also to thank my 2 students that are now starting the PhD. I think they will do very well. And this is my group of students. Thank you.
We have time for a couple of questions. Anything hexagonal shared space hacking?
For when you start the first line that you set up on the border, you start from a corner, and you cannot start from when you have it like that, so you cannot start here. You must the corner.
There is always a circle in one corner, so that's a given. Maybe you can have configuration that have other vertices that are not occupied, but at least one there is. So by convention, I always sit in the regular polygon on the table, and they start filling.
There is always one second there.
I might miss it, but what about the polygon with the even or odd faces? What?
They are all multiple of 6.
Yes, but did you try to put instead? I mean, okay.
Oh yeah, I have before reaching curved hexagonal packing, I did a lot of simulation with the previous paper, that was before curved hexagonal packing is this one, and I have studied from the equilateral triangle up to the hexadecagon with a lot of really plenty of configuration. And no, these nice things are all in there.
Yeah,
am I right that you're not claiming that curved hexagonal packing will give you the ground effect?
No, I'm not.
But you got some sort of shaping procedure.
No, okay. What I claim, because well, it's not approved. Up till, for example, for the dodecagon, I forgot to tell you, for the circle, 91 is the last case in which you have curved hexagonal packing as the best packing you can do. Well, conjecture by Graham-Lupacek, okay? For the dodecagon, conjecture by me, Ulises, and Mauricio, is that 127 is the best curved hexagonal packing skill that you can get, but after that you lose it, okay? dodecagon is better. I think I remember it. The dodecagon is better than the octadecagon in this respect. Okay. Of course, it's much easier to find that it doesn't work because with your program you find something that is the answer, question solved, right? I cannot give you a proof that 127 for the dodecagon is still curved hexagonal packing, but I made a lot of simulation. A lot.
And so is that limit an interesting sequence as you change the number of sides?
Yeah, it changes. It changes the threshold where you lose curved hexagonal packing changes. Of course, if you put sigma, the number of sides, very large, you tend to go to the circle. So that's cool.
Any other questions?
Yeah, but your density packing, maybe I missed that. It always doesn't. So do you fix the ratio between the radius of the polygon that you put your
The size, well, the polygon you do it the ratio you want. I mean the size
ratio
of,
between the polygon
yeah, no,
size
that's actually something here. That's actually comes of this condition. You start putting your coins and you need to end up here. This is 1/6 of your domain. So under rotation of the proper angle, this point has to go here. So this is the condition you have to meet. So this fixes the size D of your these are the centers of your disk. Okay.
Yeah.
Imagine that.
I'm just wondering, you could make this is of course then infinitely small because it just needs to be an integer number.
Oh yeah, that would change K, which is the number of shells. So look here. Well, I don't know how much you can see, but this is the non-infinitesimal, but these are very small. The number of disks that are here is the same number that is here. Okay.
So the packing fraction always depends on K, of course.
Yeah. Yes.
And then for this algorithm works when the number of sides is a factor of 6. But if you start from a corner and you divide this, then you must end up to another corner.
Yes.
It should be.
Yeah, this is just for this algorithm is just for polygons that have a number of sides multiple of 6, not for any polygon. You cannot apply it to any polygon.
All right.
Thank you.
Thank you very much.